Hi guys, in this next video, we're going to talk about what orbitals kind of look like when they participate in chemical bonds. So we know that electrons are found in orbitals, and it's specifically the valence electrons that participate in bonding. So what happens is the valence electron orbitals, they overlap with each other. Now, in more complex molecules, when the orbitals overlap, they kind of mix together or hybridize. And when they do that, they change a little bit. Their shape changes and their energy changes to make a shape that's more stable. And because it's more stable, it's going to have a lower energy. Okay, so an example here is a CH4 molecule, and I'm going to show you some pictures on the next page. So we remember from the atom unit that s orbitals have a spherical shape, and the p orbitals have a dumbbell shape. Okay, so when the s and the p orbitals overlap, we get a new shape. So notice that this shape here doesn't match a sphere or a dumbbell perfectly. It's a new shape. And that new shape is more stable and it has a lower energy. Okay, so what you guys are going to have to be able to do is figure out which orbitals are overlapping and say what the hybridization on the center atom is. So for CH4, we have an S and three P's overlapping. So we say that the hybridization is sp3. And I'm going to show you how to do that based on your Lewis dot diagrams. So we're going to go ahead and go to the next page. So guys, these are your options when you're asked about what kind of hybridization a molecule has. So it could either have sp, sp2, or sp3. There are hybridizations that are more involved than this. They include d orbitals, but you guys don't have to worry about those because those are your shapes that are more complicated than tetrahedral, which are not responsible for in this course. Okay, so if you have a linear molecule, then the hybridization is sp. So just to give you an example, carbon dioxide looks like this. And we're going to be looking at the carbon, which is the center molecule, right? So we know that the shape is linear because there's two things sticking off of that carbon, and there's no lone pairs to mess with the angles. So whenever you have two things sticking off the center atom, that's how many things have mixed together. So you have an s and a p orbital, 1 + 1 = 2. Okay. Same thing goes for something like this. So technically in nitrogen, you don't have a center atom, but when you only have two atoms bonded together, their shape is linear. So you can say that it's an sp hybridization as well. Okay. Now sp2 means you have three things sticking off of the center atom. You have an s and a p and a p. So that's three things on center atom. Let's write that same thing here. S plus P equals two things on center atom. Okay, so what you want to look for is that trigonal planar geometry. And we're talking about the electron domain geometry, guys. So whether it's three atoms sticking off of the center or two atoms and a lone pair. So my examples for you are BF3, So my fluorines are going to be surrounded by lone pairs, but when we're talking about hybridization, we're looking at the center atom. So boron is the center atom. It's got 3 things sticking off of it, so sp2 would be your hybridization. This also works for sulfur dioxide. And I'm just drawing these quickly, guys, because I know you know how to draw them already, but I want you to have some images for your examples. So this is also trigonal planar because we have 2 atoms, we have 2 oxygens sticking off of the sulfur, and this lone pair up here. Okay, so 3 things sticking off is S plus P plus P plus P. So it's an sp2 hybridization. You have an s orbital overlapping and 2 p orbitals overlapping. Okay, finally, guys, sp3 is an s plus an p plus a p plus a p, which means to have sp3 hybridization, you need 4 things sticking off the center atom. And again, guys, when we say tetrahedral here, we're talking about the electron domain geometry. So it could be 4 atoms sticking off, or 3 atoms and 1 lone pair, or 2 atoms and 2 lone pairs. Okay, so just to give you some quick examples, CH4 is nice and easy to draw. There's 4 things sticking off of the center, this carbon, so it's sp3, right? Same thing would be for pH3. When I draw out pH3, it's got 3 hydrogen atoms sticking off of the P and a lone pair. So that's a total of 4 things. So we would say it's an sp3 hybridization. Okay. One more visual of this, guys. So they're showing us an ammonia molecule, an NH3 molecule. And again, nitrogen has 3 hydrogens sticking off and a lone pair. So the electron domain geometry is tetrahedral, which means we need 4 things, an S and 3 Ps. That would be my hybridization. All right, so again, guys, you're just counting what's on the center atom. Okay, now based on how these orbitals overlap, we call them either sigma bonds or pi bonds. So now when you draw a molecule, you have to know its shape. You have to know what kind of hybridization exists in that molecule. You also have to be able to count how many sigma and pi bonds there are. So for sigma and pi bonds, we're talking about how the dumbbells, how the p orbitals, how they overlap. So for a sigma bond, it's an end-to-end overlap. So here's my one dumbbell, and the other one would overlap it like that. So that overlap is a sigma bond, okay? And they show that to us down here too. So this is a big complicated molecule. It's a C2H4 molecule, and there's a sigma bond where we have this overlap on the ends of the dumbbells, okay? A pi bond is a side-to-side overlap. So again, I have my p orbital is like my dumbbell shape, and it's gonna overlap next to that p orbital. Okay, so that here is your pi bonds. We have these 2 orbitals overlapping with each other, and these 2 orbitals overlapping with each other. Okay, so that would be right here. And the symbol for pi is this pi sign. Okay, so guys, this picture looks very confusing. There's a very simple way to count how many sigma and pi bonds are in a molecule. So that 3D picture really shows the shape and shows them overlapping. But this is what we're used to. This is what we're used to looking at. We'd be drawing the Lewis dot diagram, and the Lewis dot diagram would look like this. That's nice and simple. This is called a ball and stick model. So if we build models in class, if we ever get to do that, that's what it's going to look like. So the rules for counting sigma and pi bonds. If it's a single bond, it's a sigma bond. If it's a double bond, you have a sigma and a pi bond. And if it's a triple bond, it's a sigma and 2 pi bonds. Because you have, so in each one, you have more and more stuff overlapping. So if I were to look at this molecule, right, I have 4 single bonds in this molecule. Those single bonds are here, 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 and here. So that means I have 4 sigmas. And then I have this double bond in the middle. So one double bond is a sigma and a pi. So in total, what do I have in this compound? I have 5 sigma bonds and 1 pi. And that would be my final answer. So this is something that you guys wanna remember, okay? I want you guys to give this one a try. So again, we didn't give you like really nice pictures here, but this is showing you the orbitals overlapping when you have a triple bond. So I'm going to draw this for you. This is carbon with a triple bond and a hydrogen on each side. So I want you guys to look at this molecule and I want you to tell me how many sigma and pi bonds are in it. Okay. All right, finally, guys, we're going to end this video by talking about bond strengths. Okay, so when we talk about bond strengths and energies, we're talking about single bonds versus double bonds versus triple bonds. So notice that the amount of electrons being shared are different. When you look at single, double, and triple bonds, their sizes are different. Single bonds are long and they're actually the weakest. And as you move towards a triple bond, you become stronger. So the bond gets shorter, the atoms are closer together, and the bond is stronger. So like something with triple bonds in it is going to be harder to break apart than something with single bonds in it. Okay, so this is just another chart showing you examples of atoms that can have single, double, or triple bonds between themselves. So like if we look right here, carbon can have a single, a double, or a triple. So we notice that as we move down to the triple bond, the bond length gets shorter. They're giving you the actual sizes here, right, in angstroms. So this is much shorter than this. And then we're going to know that this bond is going to be weaker than this one. This is going to be our strongest. When we compare C bonding to N, again, single bond is long, triple bond is shortest, and we go from weak to strong. Right? Same thing here, weak to strong. Right? Nitrogen, bond gets shorter, weak to strong. Nitrogen to oxygen, so there's no triple bond available there. Your single bond would be weaker than your double bond shorter, and for oxygen as well. Okay, so this is just some evidence of how the length and the strength of the bonds are related. So The other thing, I guess, guys, that we just need to say, these two little notes down here just kind of say what we've been talking about. So when we think about like bond strength, the stronger a bond is, the more energy is going to be required to break it. So when we break a bond, energy always needs to be absorbed, but the stronger it is, the more we're going to have to put in to break that bond. Okay, so you'll be asked to compare bond strengths based on the type of bonds we have. All right, so that's it for today, guys. We're actually done with covalent bonding after today. Our next video is going to talk about how molecules, separate molecules containing covalent bonds, how they're attracted to each other. All right, so here's a last question, and I'll see you guys tomorrow.